From towering structures to wave-breaking defenses, modern construction blends precision and power, shaping resilient concrete works that transform coastlines and cities alike. Continuous flight auger piling is a modern and highly efficient technique for constructing cast-in-place concrete piles using a hollow stem continuous auger. This method has become increasingly popular in urban and environmentally sensitive construction sites due to its low noise, minimal vibration, and rapid installation speed. The CFA system delivers both precision and continuity, allowing piles to be formed quickly while maintaining excellent ground stability throughout the process. The construction sequence begins with the drilling phase, during which a continuous flight auger is rotated downward into the soil. As the auger advances, its flights transport loosened soil upward, effectively forming a stable borehole without the need for temporary casing or drilling fluids such as bentonite. The hollow stem of the auger plays a crucial role in facilitating the next stage of the process. Once the design depth is reached, drilling stops, and the system transitions seamlessly into concrete placement. During concrete pouring, the auger is extracted at a carefully controlled and constant rate. At the same time, high-quality concrete is pumped through the auger's hollow stem, filling the void created by the auger's withdrawal. Because concrete pressure is maintained continuously, the borehole remains supported at all times, preventing collapse and ensuring the formation of a uniform, defect-free pile shaft. This simultaneous extraction and casting process is what gives CFA piling its distinctive, continuous character. Following concreting, the next essential step is reinforcement installation. A steel reinforcing cage is lowered into the fresh concrete, either immediately after the auger has been fully removed, or gradually as extraction progresses, depending on the project's structural requirements. The fluidity of the newly placed concrete allows the reinforcement to be inserted smoothly and to settle into its correct position, helping the pile achieve its designed load-bearing capacity. CFA piling offers several major advantages. One of the most important is its quiet and vibration-free operation, which makes it exceptionally well-suited for densely built areas, sites near existing structures, and locations where ground vibration must be minimized. The method is also extremely versatile, performing effectively in a wide range of soil conditions, from cohesive clays to loose, non-cohesive sands, without relying on supporting fluids or casing systems. In addition, CFA piles can be installed rapidly, as the drilling and concreting operations are continuous and automated, enabling high production rates and improved project efficiency. Finally, the system is considered environmentally friendly because it causes minimal disturbance to the surrounding ground and generates less spoil compared to other piling methods. Altogether, the CFA technique provides a reliable, economical, and clean solution for deep foundation construction in modern civil engineering. The construction of the third Bosphorus Bridge, opened on August 26, 2016, showcases the outstanding efficiency of modern slipform engineering. Located near the Black Sea entrance, this landmark structure links Asia and Europe across the Bosphorus Strait. Its massive pylons, featuring a triangular cross-section and 1.50-meter wall thickness, were built using an advanced slipform system specially designed for continuous vertical concrete placement. After the slipform assembly and startup, the formwork climbed steadily as fresh concrete was poured, enabling uninterrupted progress and exceptional structural accuracy. This method provided significant time savings and ensured uniform surface quality throughout the towering shafts. Rising to 322 meters, the Yavuz Sultan Selim Bridge stands today as the tallest suspension bridge in the world and the second tallest bridge of any type, demonstrating the remarkable capabilities of slipforming technology. The installation of precast concrete columns using bolted connections offers a fast, safe, and highly efficient construction method. At the precast plant, column shoes are cast directly into the column, while matching anchor bolts are accurately positioned in the foundation using simple installation templates. As a result, precasters benefit from effortless assembly inside the molds, and contractors enjoy rapid erection on site. When the column is lifted into place, workers align the shoes with the anchor bolts and tighten the nuts, creating an immediate and stiff connection without the need for temporary bracing. This means each column can be securely installed in about 10 minutes, allowing the crane to move to the next lift without delay. The system reduces manpower requirements to only a crane operator and 2 installers, saving valuable time and ensuring reliable performance even in seismic regions. Caisson Relocation using roller airbags and ship-launching airbags provides a low-cost, low-risk solution for transferring heavy caissons onto a semi-submersible barge. Instead of relying on fixed-track systems, the inflatable rollers create a flexible, continuous support surface that adapts to uneven loads and ground conditions. As the caisson is gradually jacked up, roller airbags are positioned beneath it, allowing smooth, controlled rolling toward the barge deck. Ship-launching airbags then stabilize and guide the final positioning. This method is widely used for small and medium vessels, helping shipyards improve productivity while reducing energy use, manpower requirements, and overall investment. Precast concrete cap beams are transported to the temporary lock chamber in Harelbeke and carefully lifted into place using a crane mounted on a barge. Precise positioning is essential to ensure proper alignment with the foundation elements and compliance with the overall design specifications. This controlled lifting and installation process guarantees structural accuracy and supports the efficient construction of the temporary lock. A 360-ton steel bridge was installed as a key element of the Tilbury to approach bridge for Forth ports. After being fully assembled in Rotterdam, the bridge was towed 135 nautical miles to the Tilbury 2 site in a 24-hour operation. Upon arrival, lifting preparations began by lining up the heavy lift vessel Matador 3 alongside the H332 barge. The bridge was then carefully raised in an initial lift and maneuvered toward its final location. As the structure was brought into position, precise coordination ensured that alignment and placement met all engineering requirements. Finally, the bridge was set down securely, completing the first of 3 major components for the new roll-on/roll-off terminal. The new bridge was built in a staging area adjacent to the railway, allowing work to progress without disrupting train services. Engineers assembled the steel framework on solid foundations, carefully aligning sections to ensure accuracy. Reinforcements and crossbeams were added to create a robust structure capable of supporting heavy rail traffic. The deck was installed and secured, forming a complete bridge ready for installation. By preparing the entire structure in advance, the project minimized the time required on the active railway line and ensured efficient execution during the replacement phase. Once the new bridge was fully assembled, attention turned to the removal of the existing structure and installation of the replacement. First, heavy lifting equipment was brought into position, including self-propelled modular transporters. These specialized machines were maneuvered under the new bridge, raising it slightly off its supports. The massive structure was then carefully transported along a prepared route toward the railway corridor. Precision control was essential as the bridge, weighing hundreds of tons, was moved slowly into alignment with its final position. Meanwhile, the old bridge was dismantled and lifted out, clearing the site for the new installation. After the existing structure was removed, the new bridge was rolled into place and carefully lowered onto prepared abutments. Engineers conducted precise adjustments to ensure a perfect fit and secure seating. Once in position, the bridge was locked down, and final connections were made to integrate it with the rail line. This coordinated effort allowed the replacement to be completed within a limited time frame, minimizing disruption to rail services and ensuring the new bridge was ready for operation. The construction of the Waikato River Bridge showcases a carefully planned and environmentally responsive engineering process. Spanning the mighty Waikato River, the bridge was delivered through a collaboration between HEB Construction, Hamilton City Council, and the New Zealand government. Throughout the project, crews followed a staged approach that minimized ecological disturbance, especially to the habitat of native long-tailed bats. The 4-lane structure, which includes dedicated bus lanes, measures 180 meters in total length and features a 96-meter main span across the river. Construction began with earthworks and foundation works on both riverbanks, followed by the creation of the unique Y-shaped southern pier. This single support allowed the team to avoid placing any piers in the water, significantly reducing environmental impact. Precast segments and steel components were progressively lifted and assembled, forming the superstructure that now links Peacock with Hillcrest and the eastern suburbs. As the time-lapse shows, each phase was executed efficiently, resulting in a modern, resilient, and ecologically sensitive bridge that strengthens regional connectivity. The construction of the concrete pavement at Takasago Wharf and Sakata Port represents a highly coordinated, large-scale civil works operation that integrates precise material handling, advanced paving machinery, and strict quality control procedures. The process begins with the delivery of ready-mixed concrete to the site using dump trucks. These trucks transport the concrete from the batching plant to the paving area while maintaining optimal consistency and setting time. Upon arriving, the dump trucks position themselves alongside the active paving zone and discharge the concrete into the designated receiving area. Care is taken to unload the material efficiently so as not to interrupt the continuous paving flow, which is crucial for large slab sections. The concrete is offloaded in controlled quantities to ensure a uniform supply for spreading and subsequent operations. Once the concrete is discharged, an excavator, commonly referred to as a backhoe in Japan, begins the initial spreading operation. This step, known as makidashi or rough spreading, involves using the excavator bucket to distribute the freshly delivered concrete across the subbase. The objective is to create an even layer with appropriate height and width so that subsequent machines can work effectively. The backhoe operator carefully adjusts the volume of concrete in different areas, preventing excessive accumulation while ensuring complete coverage of the paved section. This preliminary distribution significantly reduces the workload of the mechanical spreaders that follow. After the rough spreading is completed, a concrete blade spreader moves into position. This specialized machine automatically levels and spreads the concrete to a more precise thickness. The blade spreader uses adjustable blades and augers to push excess material forward while filling voids across the paving width. Its purpose is to create a uniform, consistent layer of concrete that meets the specified grade before compaction. The spreader operates continuously in sync with the concrete supply, ensuring a smooth workflow without cold joints or interruptions. This stage marks the transition from manual distribution to mechanized paving, a major factor in achieving uniform pavement quality. Following spreading, the concrete undergoes compaction using internal and surface vibrators. Vibration is essential to eliminate entrapped air, increase density, and ensure proper bonding within the mix. In large-scale paving projects like Takasago Wharf, high-frequency vibrators are embedded along the paving line, delivering consistent vibration across the slab. Operators monitor the compaction results to avoid over-vibration, which can cause segregation, or under-vibration, which results in voids. Proper compaction ensures the durability and structural performance of the pavement, especially under heavy port loads. Before finishing the upper surface, deformed reinforcing mesh is installed in the concrete. This steel reinforcement helps control cracking caused by temperature changes and long-term loading. Workers carefully place the mesh panels at the appropriate height within the concrete layer, ensuring adequate concrete cover both above and below the mesh. The reinforcement is aligned accurately to maintain structural continuity across the entire slab. This step is synchronized with the paving progression so that reinforcement placement remains ahead of the finishing equipment. With reinforcement in place and the concrete properly compacted, A concrete finisher machine takes over to create the initial textured surface. The finisher smooths, levels, and shapes the pavement while removing surface irregularities. This machine typically includes oscillating beams or screeds that strike off excess concrete and ensure consistent elevation. The objective at this stage is not to achieve the final finish, but to establish a uniform plane that prepares the slab for finer adjustments and leveling. The next stage involves a longitudinal finishing machine, often referred to as a leveler. This equipment performs precise grading and surface smoothing along the direction of pavement placement. Using automatic sensors and leveling systems, the machine corrects any remaining deviations in elevation. This longitudinal finishing ensures that the slab meets strict dimensional tolerances and geometric requirements. For port pavements, maintaining precise flatness is essential to ensure proper cargo handling operations and prevent water accumulation. Once the surface is shaped, joints must be created to control concrete shrinkage. At Takasago Wharf, a vibrating joint cutting machine is used to form contraction joints directly into the fresh concrete. These joints, known as uchikomi mechi, are installed immediately while the concrete is still plastic. The machine vibrates a steel plate or blade through the concrete to create a clean indentation that will later function as a crack control joint. The vibration ensures the joint is fully integrated without disturbing the surrounding concrete mass. After the contraction joints are installed, workers place transverse joint slate boards across the pavement. These boards help maintain uniform spacing between slabs and provide clean boundaries for the joints. The installation must be precise so that structural discontinuities develop at the specified locations as the concrete cures. Proper jointing is critical for preventing uncontrolled cracking and maintaining long-term pavement performance. To protect the concrete and promote proper curing, a membrane-forming curing compound is then sprayed over the entire surface. This compound forms a thin film that prevents the rapid evaporation of water from the concrete, ensuring adequate hydration during the early stages of curing. Workers use spray equipment to apply the compound uniformly, paying particular attention to edges and corners where evaporation can occur more rapidly. In areas requiring smoother finishes, hand troweling is performed. Skilled workers use steel trowels to refine the surface, remove minor imperfections, and achieve localized precision. Following troweling, a brush finish is applied over selected zones. This broom or brush finish produces fine, uniform grooves across the surface, improving skid resistance and providing safer operating conditions for vehicles and equipment. The brush finish is typically applied perpendicular to the direction of traffic flow to optimize traction. Once finishing is complete, curing mats are placed over the pavement. These mats help retain moisture and protect the surface from direct sunlight and wind. Workers ensure that the mats overlap adequately and cover the entire slab. Following mat placement, a series of controlled water sprinkling operations is carried out. This wet curing phase maintains the concrete at ideal moisture levels, further enhancing strength development and durability. In port projects, proper curing is especially important due to exposure to marine environments and heavy mechanical loading. As the paving progresses from one section to another, the large paving machines must be relocated. Using a crane, workers safely lift and reposition major equipment such as spreaders, finishers, and levelers. The fabrication process begins with the assembly of the formwork. Large formwork panels are lifted and positioned by a crane, allowing workers to join them safely and accurately. The main panels assembled on the ground are connected using taper pins, cotter pins, and cotters to ensure tight, stable joints. Once the body of the formwork is secured, the end plates are installed to complete the mold's geometry. A working platform is then attached to provide access for the upcoming concreting operations. Before any concrete work begins, the inner surfaces of the formwork are sprayed with a release agent to ensure clean demolding. Fresh concrete is delivered by a truck agitator, which transfers the mix into a red concrete pump positioned near the casting area. During rainy weather, a protective sheeted frame is erected to prevent rainwater from entering the mix during pumping and placement. Concrete is supplied through the pump's discharge hose, and thanks to the rain protection frame, the mix remains uncontaminated even during wet weather. Access to the casting point is provided by ladders, and workers wear safety harnesses throughout the operation because the tetrapod height reaches approximately 4 meters. Concrete is placed into the formwork in 4 layers. For each layer, internal vibrators are applied to consolidate the mix, remove trapped air, and ensure dense, uniform filling. Each leg of the tetrapod is assigned a worker responsible for proper vibration. The upper layers are placed and compacted in the same manner until concrete reaches the top. When the formwork is fully filled, protruding latents and excess concrete at the mouth of the pump hose are carefully removed. Before finishing the top surface, a tool called Tupika is used to eliminate surface air pockets, greatly reducing visible blowholes. After this treatment, a curing compound is sprayed over the top surface. Finally, a cover is placed to prevent rapid moisture loss, marking the completion of concrete placement. Once the concrete reaches the required strength, formwork removal begins. A crawler crane is used to lift and detach the mold components. The removed formwork is then brushed and cleaned thoroughly to prepare it for the next casting cycle. After cleaning, the panels are reassembled for repeated use. The exposed tetrapod is coated with a membrane-forming curing agent. This curing method creates a protective film on the concrete surface, preventing internal moisture from evaporating too quickly and ensuring proper strength development. The curing agent is applied uniformly over the entire surface, completing the fabrication process. The production of the T3 concrete tetrapod in the M-Constructor metal mold follows a streamlined and controlled process. First, the precisely assembled steel form is filled with high-quality concrete to ensure uniform density and structural strength. After adequate curing time, the mold is opened, allowing careful demolding without damaging the fresh surfaces. The finished T3 unit then emerges with accurate geometry, smooth faces, and consistent dimensions, ready for use in coastal protection and wave energy dissipation structures.